Okay, ladies and gentlemen, here we are. Okay, now, graphing logs, exponentials, um, the graphing of logs and exponentials is pretty straightforward. It's really not a heck of a lot of excitement there, but inverses can get rather goofy looking and get unusual. We will deal with those last, but logs and exponentials, the best way I can say to you to graph a log and an exponential, first of all, you have to know how they look. In general, log graphs look like this. Okay, so we have a vertical asymptote at 0. Okay, and the graph continues all the way in the positive direction. So my range would be, okay, however, my domain is what? Greater than, than 0. Okay, now this would be in effect your parent function. Okay, like if we were dealing with base 10, okay, log of x base 10, we'll actually drop some points in a minute and we'll kind of show you, I'll show you some shortcuts to finding, drawing your graphs. An exponential looks a lot like, so for example, a to the x, this guy also has an asymptote. And he has a y-intercept of 1. And I'll explain why all this is going on there in just a minute, but I want everybody to basically be able to find those points if necessary. Okay? All right. So first, what's my domain here? The domain and the range. Y is greater than 0. Very good. Okay. Like I said, we will do inverses last. Okay, we'll talk about that because the inverses are specific to whatever function they're an inverse of. Now, let me show you one quick thing. Here's a nice way to find some points. All right, if you notice, here we have a logarithmic graph, log base 2. And I've got, first of all, this point right here. Let me zoom in. Okay. It crosses the x-axis at 1. And the reason for that is because the log of anything, of any base, at 1 is 0. Because remember, if it was, in this case, 2 to the 0th is 1. Right? Notice, if I change this, I'm still always going to be passing through that same point, regardless of what my base is. Now, here's a problem that we have when we have a base of 1. And this is not a function. Okay? All right. And in fact, I'm going to go ahead and just change this real fast to make it a little bit bigger. All right. Now, in order to get all the way out, hi. Thank you. Okay. Shayla, this is for you. It's for guidance. You can do it now or later. Okay, that's fine. All right. Let me see if I can get in. Okay, so here we are at base 3. Now, notice where some of these points are. At 3, it's 1. At 9, it's 2. At 27, it's 3. They are the powers of 3. And if I change my base, say to something a little smaller, there you can see it. 2 to the first, 4 to the first, 2 to the second, 2 to the first is 2. Strike that, excuse me. Log base 2 of 2 is 1. Log base 2 of 4 is 2. Log base 2 of 8 is 3. Base 2 of 16 is 4. Okay? Now, what that allows you to do is kind of basically fudge your graph. Okay? So, here's how you do it. Hold on. All right. So, if you have your graph paper, okay, first, let's say I'm doing log base 3 of x, and I'm trying to graph that, okay? Now, I would first hit that spot, that x-intercept, okay? You can pretty much eyeball between 0 and 1 because you know it's asymptotic, okay? You can pretty much just get away with that. Now, to graph some points, what you're basically going to look at is 3 to the first, 3 to the 0th, 3 squared, 3 to the third. Okay? At 0, you need a point at 1. At 3, you have 1. At 9, you have 2. And that's the beautiful part about graphing logs, is because you don't need a lot of points. Because let's be honest, your graph is usually 10 by 10, and you're not going to go out that far. Okay? You only need a few points. Now, an exponential, again, same thing is basically going to apply. If, say we're doing base 3, again, it's 3 to the 0th, 3 to the first, 3 squared, 3 to the third. And now go over 1 and up 3. Go over 2 and go up 9. So there's not a lot of points that you can graph, like I said, again, before you run out of space on your graph. Okay? The one thing I don't want to see is this. No. All right, it is a smooth curve. It doesn't jump, in its slope, anything like that. Please don't do that. Okay. Also, this is an asymptote. And when you're graphing asymptotes, there are a couple of rules. One, it doesn't cross. Okay? So, if you give me an asymptote that does this, I'm going to say no. Okay? Don't do that. Asymptotes also hug the curve. The curve hugs the asymptote. So it doesn't do this. Okay? Don't do that. when you're doing your graphs, okay? See how that jumped out? Okay. Now, the math for both of these was very much the same. I mean, how I graphed those points and how I chose them is not coincidence. In fact, there they are. One is a log, and one is an exponential. Let's take this to be just 1. Wait, hold on. Where's 1? There's 1. Okay, so there I have 2 to the x in green and log base 2 in orange. Okay? And one thing that I'm doing, now notice, if I change the base, which in this case is green, the higher it goes out, so here it's 5, at each step I'm multiplying it by 5, so it goes up really, really fast. Okay? If it's small, like there at 2, it's kind of gentle, but still grows really fast. Now, I'm shrinking it, and as my base gets smaller, you can see it right up here in the left-hand corner, 1.34 to the x, or to the 1x. Here, it's 1.04 times 1.04 times 1.04 over and over and over again. So it's not growing really fast. And you can see there is a curve to it. It's just really small. See? I have to go out really far to begin to see that same ski slope kind of thing going on. But at small numbers, it's very imperceptible. And you've seen that as well on whenever you played with your calculators. It grows, but it's growing pretty slow. You know, we got to go out really far in order to turn it into a 2. You see what I mean? So a small base is a slow growth. Okay? Now, at 1, we get the constant. Hold on, I'm going to fix this so that I don't have to change so darn much. At 1, it's just a constant. Because now I'm saying 1 times 1 times 1 times 1 times 1 times 1. Okay, boring, and it's always going to be 1. Okay? But if I'm smaller than 1, now all of a sudden I get this kind of thing. And you know what? I'm just going to close this log off for a second. So this is 1/5. Well, 1/5 times 1/5 times 1/5 times 1/5, you're shrinking it by 1/5 each time, or to 1/5 of its original size each time. And so it shrinks really, really, really fast. Okay? So something smaller than 1 decreases, greater than 1 increases. And we saw this when we were dealing with sequences in series. If the geometric sequence converges, that means it's getting smaller and smaller and smaller and smaller at each step. Okay? If it diverged, it was because it was getting bigger and bigger and bigger and bigger and bigger and went off to infinity eventually. At 0, it's kind of boring. 0 to the 0 to the 0, 0 times 0 times 0 times 0 times 0 is still 0. Okay? And negatives don't exist. Okay? Because how could I say, well, in this case, that's 2/5, negative 2/5. Well, negative 2/5 to the 3rd, that's not a problem. That's negative 8/125. But what if I said negative 2/5 to the 3/7, or to the 0.52? Okay, now all of a sudden we're dealing with parts of a negative number, and we're not ready to deal with those yet because now that's dealing with crazy complex number stuff, and you wind up getting some weird things. But again, complex logarithms, imaginary logarithms, is a pretty cool field by itself. Okay. All right. All right, and this is just saying is making it grow even just faster. And again, we see now. Notice. Let's go back. Let's go to 2, base of 2, and notice with a negative exponent. A negative exponent, again, is also making it smaller and smaller and smaller and smaller, because a negative exponent flips your whole number into a fraction, which is the same thing as kind of having that smaller than 1 base again. So both accomplish the same idea, all right? If you think about 2 to the negative 2 power, what would that be? What's 2 to the negative 2? 1/4. Okay, well, saying that another way would be 1/4 to the first. All right, so again, you're basically finding two different ways of expressing the same fraction, one with an exponent and one with the number itself. The number can be smaller than 1, or the exponent can be negative, and they both become that decremental shrinking effect. Okay? All right. Better life through math. All right. Okay. So, inverses. Do you guys remember how to take an inverse?
Isn't like you put the x to the y?
Yeah. When to do that, you switch your x's and your y's. So, inverses. So if I gave you y is equal to, say, let's do 5 times 2 to the x plus 3. Okay, and I wanted to find the inverse of that graph. You guys did all this last year. You swap the x and the y, and you solve for y again. So kind of think about this as dealing kind of very much like a birthday present or a holiday gift or whatever, where you are trying to get the thing on the inside of your gift. You have to first remove the card, because if you don't read the card, then your aunt is going to kick your butt for not caring about the gift. So you read the card, and then you take off the paper, and then you open the box, and then you're basically getting smaller and smaller and smaller, closer and closer and closer to the y. So we get rid of the 5. Okay. Now, to get the y down, what would I do? How do I get that y to be full-sized? So, in order to make the exponent into a coefficient, what do I have to do? You were right. No, I have no idea. Say it again.
Okay, so like how they have 2 y plus 3? Can you do like add 2 to make that? I don't know explain that. It's like
I want to undo an exponential. What is the opposite of an exponential? A log. Yeah, well, not multiply by a log. You apply a log. Apply a log. So log base what? 2. Any log would work, but log base 2 is nice because it's going to get rid of the 2 that I have already. And log base 2 of 2 is 1. And now we can get rid of the 3. Okay? Okay, one thing about inverses is that when you graph them with the parent function, the original function, you get a certain effect. So, for example, if I did, actually I have it here already. Not this one, there's the other one. Where's the other one? Okay, so what I've done is I've graphed two functions, 2 to the 0.6x, okay? So let's work with this function, 2 to the 0.6x. 0.6 is 3/5. Now let's find its inverse. Again, getting x, moving things away from the y, we have to bust out that exponential by applying a log. Point 0.6 is 3/5. Right? Oh. And we get, all right. And now and we can also write this as log base 2 of x divided by 0.6. And the only reason why I'm not a big fan of leaving it as a decimal, but the computer left it as a decimal. So what I want to show you is that the original function and that logarithm, the exponential function and that logarithm, are inverses of each other. Okay? We cool? All right. And going back to my graph, you'll see the two graphs next to each other. And what's one thing that you immediately notice? What does that mean? Mirror each other. Use a math speak for that one, will you? Reflection about what? Y equals x. Okay. Line of symmetry is y equals x. All right. Okay. Just make sure we're not missing anything here. All right. Because multiplying by 3/5, multiplying by 5/3, 5/3, well, 3/5 is equal to 0.6, okay? So 5/3 is 1 over 0.6. As I reflected it, I flipped it upside down. I took its reciprocal. And this is not a form that I generally like. I usually, I mean, I would leave it like that under all normal circumstances, but because the calculator, this computer program that I'm using, wrote it in this form, I wanted you to see it in that form. Okay? All right. What else did I need you to see? Okay. All right. All right. All right. So, what I'm going to do is I'm going to pause the recording for just a second. Some of these, okay, yes, some of these problems are calculator problems, granted. Okay, a formula. Guys, calm down for a second. All right. Interest. Interest as well as growth and decay. Okay. The formula for all three of these is very much the same formula, just applied slightly differently. The way that I remember it, the formula might not look exactly the same. Some of the variables might have changed names, but the formula is the same regardless of whatever you're doing. You have an amount final equaling an amount initial 1 plus the rate over the number of times it's compounded times the number of times it's compounded and then time. Okay, so let me break all those down. Sorry? Final amount, initial amount, number of times compounded per unit of time, rate, and time. Sorry, my handwriting got caught you. All right. So if you're dealing with something compounded quarterly, that would be 4 times a year, and your n would be 4. Okay? If you're dealing with something compounded yearly, then it would just be 1. Okay? If you're dealing with something that compounds monthly, obviously it would be 12, n would be 12. Okay? Does that make sense? Seen some of these?
Do we
Okay.
always use years?
Pretty much you do, unless otherwise specified. You know, but no matter what, even if it wasn't years, you could probably expand it out to years, and your n would change. Okay. All right. Now, your growth and decay models are exactly the same, except that they're not compounded the same way. They compound differently. Okay. So, for example, we know that if you compound, let's just say you're going to open up a bank account at my bank. Okay, I'm opening up a bank and I'm offering 10% per year. Okay. Well, if I say to you I'm only going to compound once per year, yearly, so simple interest really, then if you deposit $100 on January 1st, on December 31st, I'm going to put $10 in your account. Okay? Boring, but it'll grow. And then the next year, it's 10% of that. So $11 gets thrown in there. Okay. Now you know that if you compound, because you took all this last year in Algebra 2, right? Has anyone not ever seen this in Algebra 2 or anything else? Granted, Algebra 2 was a long time ago. Even if you, I hope, Lie to your teacher. Say yes. Oh yeah, great. Glad everybody knows it. Fantastic. All right, great. So, even if this is like ancient material and you haven't seen it for a million years, compounding more often is better. Have we seen this before? We're all familiar with this concept? Or do we need to go through it real fast? Okay, let's do one example. Let's take my $100 deposit, 10%, simple interest, and then we'll compound it, okay? So $100 initial. So this is my amount initial, okay? And my number of times compounding is once per year, so simple interest. For the record, simple interest sucks. It's lousy. You don't want it. And we're going to do it for, say, 3 years. Okay? We good? And then we're going to use the same math, but now I'm going to compound twice a year. Oh, and it's a 10% rate. Okay? All right? We good? Fantastic. So let's crunch the math and see which one is better. Well, 1.1 to the third is going to be 1.331. So at the end of a year, at the end of 3 years, you will have made would have made $33.10 of profit, which would have come out to a grand total of $133.10 sitting in your account. Okay? Okay, fine. You make 33 bucks. No problem. Now we're going to do the exact same thing, but instead of compounding once a year in simple interest, I'm going to compound every 6 months. Okay? But the rate is still going to be 10% per year. So in order to deal with the fact that you're compounding more than once, your rate at each compound is reduced. Let me show you. You see, it's that instead of getting 10% each time, you get 5% each time, so that the total is 10% for the whole year. Okay? Because basically what we're doing is we're taking the calendar and we're chopping it up into pieces, and we're just compounding it at each time, but the amount of your rate is proportional at each step. Okay? So let's do this. So 100. This is 1 plus 1 all over 20 times to the 6th. And 1.05 to the 6th power oh, wrong one. 1.3400956. Which, of course, would just be a penny, $134 and a penny. Okay, because we're not going to deal with fractional pieces of a cent. Okay, so just by splitting up the year into 2 pieces, we grew a little more. Not a lot. I mean, this is a small example. But if I were to say compound every month, okay, you don't have to copy this one down, but we'll try. I'll just do the math real fast and you can see. I don't have my glasses. Hold on, sorry. So doing it monthly got me a little bit more. See what's going on? Okay, so now what we're going to do is we're going to take this example and we're going to go to the extreme. Instead of giving you 10% of your money, I'm going to give you 100% of your money. That's a really good bank account, people. Don't tell your neighbor. Okay, no. All right, so imagine that. Imagine what that would do. Okay, imagine if I said amount final is equal to the amount initial 1 plus 1 over n to the nt. Okay? That's a really good bank account. At the end of a year, you just got $100. If you, I mean, now you're sitting with $200 at the end of the year, even if you just compounded once. Now, if I compounded twice, it's even better, right? And if I compounded monthly, that would be even better. What if I compounded daily?
Yes.
Oh yeah, that would be like awesome, wouldn't it? It's just like boom, 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 every time. I mean, let's think about that, just for giggles, just for giggles. What would that do? If I had $100 in a bank account, compounded daily with a 100% return rate, okay.
I would have to go to school.
That would give you $271 a year and 46 cents.
Because then we're going to double 46 cents.
No. I said it would double. You'd have 100% in a year.
Oh,
Right, but because, and that was if I simple interested. Okay, if I only compounded once. So, you know, you put $100 in January 1st, and on December 31st, I drop another $100 in your bank. So basically, you're getting 200% of your money. Does that make sense? Okay? But by compounding it more often, I actually got more than $200. I got $271.46. Yes. Next year's even better because then again, you would still, I mean, if I did that again, $738, $36, give or take. Okay, right. So what's happening now is I'm growing really, 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 really fast. And let's just say I didn't even compound daily. I compounded by the minute. It would even be better, right? And in fact, what's happening is that this number right here, 1 plus 1 over n to the n, approaches a value. And we'll see that. Let me show you what I'm talking about. Look. If I compounded basically roughly 3 times a day, okay? That's the new rate per year. If I do it for even bigger, 100,000 times a year. It didn't change very much, did it? It went from 2.717 to 2.718. It didn't change a lot. Even by doing it 100 times more often, it still didn't change it very much. We are approaching a value, and that value that we're approaching is E. E. E is the exponential. E is the base of the natural log. It is an irrational number. It is a very, very special number. This number is found all over nature. This number is the number that we use when we're growing things constantly. Okay? When we're talking about continuous growth, continuous growth is along the line, this whole thing turns into amount initial e to the t. That's if it's growing continuously, okay? Now, sometimes things aren't growing as fast as they possibly could. Like there are other factors involved. Like for example, so you have like bacteria growth uses formula like this. Okay, things like the radioactive decay that happen all the time. Okay, they don't happen like you're not looking at a block of plutonium and then wait a couple thousand years and then all of a sudden poof, half of it is turned into polonium. No, it doesn't work like that. It's a slow process. But if we were to look at it every 3,485 years, half of it would be gone. Okay, that's how half-life works. But so yeah, if we took snapshots of it, it would be halved each time. But in effect, what's really happening is that it's slowly decaying. Same thing with a bacteria colony. Okay, yeah, if you were to look at one bacteria 1 second, and then another second later you've got 2, another second later you've got 4. Well, that's fine with really small numbers, but as things get bigger and bigger, they're not always multiplying at exactly the same time, right? Some are multiplying, some are just finished multiplying, other ones are beginning their process. So it's a continuous thing where the number's always growing, much like our debt, okay? So we have constants that are involved in these things. For example, you could have, an amount final is equal to an amount initial e to the, say, 0.3t. Okay? Now, let me ask you something. Which one grows faster, the one on the left or the one on the right? The one on the left grows faster. Plug in 10 years and see what happens. It's e to the 10 versus e to the 3. Thank you. Thank you. Okay. All right. So, we good? Well, we got about 10 minutes, right? Okay, good. All right, so if I was to look at something and say, all right, if something is growing at a certain percentage per unit time, okay, let's just say we're having something grow at 5% per year, okay? What you're talking about now is that would be 5% growth per year. Hint, hint, wink, wink. Look at number 1. I think you can do number 2 already. I think you can do number 3. I think you can do number 4. Number 5 is old material. We did the, and in number 6, when it says per annum, that means per year. I think you have all the tools in your fingertips to solve all of these problems now. But now is a good time to ask questions. All right. We only have a few minutes left, so I'm going to kill the recording so we can answer questions. This episode of The Ronco Show has been brought to you by Exponential and Logarithmic Growth.